Welcome back to Ember Training. In this module of training, we're going to discuss more basic ZigBee concepts, including ZigBee node types, PANIDs, including extended PANIDs, and addressing. So let's start with node types. First, ZigBee has three types of basic node types that we generally talk about. There's the coordinator, or ZC, the ZigBee router, which I'll abbreviate ZR, and the ZigBee end device, ZED. And the differences between these types of devices mainly comes down to how they interact with other nodes in the network. First, we have the ZigBee coordinator. The coordinator is essentially just like a router, except it's unique in the fact that it's the first one in the network, because it's responsible for forming the PAN itself, the personal area network. So, in the virtue of being the one that starts the network, there can only ever be one coordinator at any given time. So, it's not possible for anybody to really join the network as a coordinator so much as it's possible for them to form one. So basically, in the simplest sense, the coordinator is a lot like any other router, in that after the network is formed, the coordinator doesn't really act very differently than any other router would. Now, there are some other variations we'll talk about with regard to security in future presentations that make the coordinator a little bit more sophisticated than simply just another router, but we'll revisit those again later. So for now, just assume that the coordinator is a lot like a router, except it's a special device that happens to be the first one on the network. So this brings us to a discussion of, well, what is a router? A router has the ability not only to send and receive its own packets, but also to relay for other nodes in the network. So because other nodes rely on it to do routing, it's not available for duty cycling, meaning the router can't go to sleep and wake up at various times because other nodes are depending on it to get messages through the network. So if you want a device that duty cycles, you'll have to look at end devices. End devices are devices that don't participate in any routing. So really the only concept of routing that they have is to send things to their parent or get things from their parent. And when I say parent, I mean there's some router node, potentially the coordinator, that is going to be responsible for that end device. So it bears the responsibility of forwarding messages out and proxying messages in for that device. And each end device relies on that one parent for communication to the network. If that communication is lost, the end device then has to go out and find a new parent device. It has to reattach itself to the network through some new kind of parent. Now, in future diagrams through these presentations, you'll see circles of different types. The thick red circle corresponds to the coordinator, so the special router that initiated the network. The thinner red circle corresponds to the router, of which there can be several. And the blue circles correspond to end devices, of which there can be several. Now, tying these back to stack concepts, in terms of how does one determine the node type, the node type is chosen in at least Ember's EmberZNet stack via the form network and join network API calls. So if you have an Ember form network or EasySP form network call in your programming API, those things are the things that determine whether or not the node forms a network and thus becomes a coordinator, or it joins a network as some other node type. So the node types cases are shown below. We have the Ember router, which is just a basic router node, the Ember end device, which is the most basic kind of end device that doesn't do any duty cycling at all, and the advantage to the Ember end device is that because it doesn't duty cycle, the parent knows that it can send messages directly to the child. So the child doesn't have to ask for the messages, it doesn't have to poll. Now, a sleepy end device, because it's got the ability to duty cycle essentially any time it wants, the parent doesn't know when it's okay to send things to that end device. And so the end device that's sleepy needs to poll the parent to receive its messages. It also needs to poll if there are any acknowledgments coming back from things that the child has transmitted. So if the sleepy end device sends out a message, it goes through the parent, and when the acknowledgement comes back, the child has to poll a short while later to pick that acknowledgement up. And if there are any application level responses arriving for the child, that child end device has to poll the parent yet again to receive those messages. If there's nothing there when the end device polls, then the end device can just go right back to sleep and not use any other additional battery power. So the sleepy end device is sometimes also referred to as an RX off when idle end device, meaning the receiver is turned off automatically anytime the stack is idle, not doing anything. And this is all managed internally inside the EmberZNet stack. So you don't have to worry about when to shut the radio off or turn it back on. All of that is handled by the internal stack code. Then there's a special kind of device here, an Ember mobile end device. And this is an EmberZNet specific variety, meaning that it's something that Ember supports outside of the ZigBee specification. So it doesn't break compliance, but it's not going to necessarily get all the benefits if you use it with non-Ember devices in a network. And the idea behind the mobile end device is that this is a special variant of the sleepy end device we created that is intended to be construed as mobile, in that it times out of its parent's child table very quickly. Now, normally, an end device stays in the child table of the parent, meaning the parent will track the information about the end device for very long periods of time, several minutes, customizable up to hours or days or even weeks. But in the case of the mobile end device, the assumption is that that end device will move around the network fairly regularly, and therefore the parent shouldn't get too attached to it. So where normal end devices can stay around for minutes or hours or days or weeks at a time, the mobile end device is assumed to be gone if it doesn't contact the parent within a few seconds. Okay? And these timeouts that I'm referring to are all customizable inside the stack configuration. So that's the mobile end device. It's stored in a temporary fashion on the parent to allow the device to move around more flexibly without a lot of repercussions on the parent side. Now let's talk about PANIDs. The PAN, or Personal Area Network, is separated by other networks through its PANID, its PAN identifier. And this is a 16-bit identifier that all nodes in the same PAN will share. So it's something akin to a subnet mask in the Ethernet world, in that you generally would only be communicating with devices within your local network, within your PAN in this case. And so this value is placed into the low-level MAC layer header frame in every outgoing packet, which allows devices that receive the packet to filter out the messages that don't pertain to their network. So they can look at the PAN ID, compare it against their own PAN ID, and decide, is this a message from someone in my network, or is it a message from someone on a different network that just happens to be on this channel? So I happen to hear it, but I'm not going to spend any effort decoding or decrypting it because it doesn't pertain to my network. Now, the PAN ID is chosen by the coordinator upon network formation, but because the PAN ID is the distinguishing factor between one network and another, it should be random to ensure its uniqueness. So in other words, we recommend that you select some kind of random 16-bit value for your PAN ID that keeps your network from coinciding with any other networks that happen to emerge in the area. Now, if you did happen to pick a PAN ID value that was in conflict with something else in the network, suppose you picked a value that was random and didn't appear to be in conflict, but then later another network grew to overlap with yours, and now you have two networks that conflict with each other potentially. If that ever happens, the stack can in fact detect these conflicts and can update its PAN ID automatically and inform all the nodes in its network to move to a new PAN ID. So it's able to contact only the nodes in your original network and exclude any of those nodes on the conflicting network. So you may be wondering, how does it do this? Well, it's done through the use of what's called an extended PAN ID. While the normal short 16-bit PAN ID is transmitted over the air in all of the packets because it's short and simple, the 64-bit PAN ID is still known to all the devices but is rarely ever transmitted over the air. So this is also unique for every PAN, and it's basically used as a backup criteria when the 16-bit PAN ID is not enough to distinguish one network from another. For instance, when a PAN ID conflict occurs and you want to notify all of the devices in your network to move, the way that you distinguish your network from another network is those devices in your network all share the same extended PAN ID, which is unlikely to ever conflict because it's a 64-bit address space rather than a 16-bit address space. So the extended PAN ID is 64 bits. It's also chosen by the coordinator during network formation. It's only sent over the air during what's called an active scan when nodes are soliciting the network for devices in the area. And it's also a useful factor in allowing you to select a network. So if you are on the other side of the story and you're trying to come into a network rather than form one, you might wonder, how do I tell which networks are available? And the way that the networks are distinguishable from one another is not only the PANID, but also the extended PANID. So you might want to do something special where you decide you're only going to use a certain subset of PANIDs or set certain bits in your extended PANID such that you can distinguish your networks from other networks. Because if the extended PANID is completely random, then it's not a very good selection criteria. But just don't limit yourself too much, because the more you limit this, the more likelihood you have of a conflict. And if your extended PANID ever conflicts, there's really nothing you can do to fix that concept, because the extended PANID must be unique between two networks. Okay? So it's a little like a Wi-Fi SSID, except those can be the same between networks, and this can't. So the other types of things that distinguish nodes from one another, in addition to their network-wide criteria of PANID and extended PANID, are their individual node addresses. So the node has, much like a short and long PANID, also a short and long address. So the long address is the IEEE assigned MAC address, or EUI64. The EUI64 is a 64-bit address that is globally unique, meaning no two IEEE-based radios in the world should ever have the same EUI64. So this is something generally assigned at manufacturing time. In the case of Ember's chips, these are assigned when the chips come out of our factory before they arrive to you. But the concept is this would be set at manufacturing time and never changed. And that's how you tell one radio from another. But much like the extended PANID, because this is a fairly large quantity of 8 bytes rather than 2 bytes, it's not sent over the air very often. So in cases where data needs to be kept regarding addressing, most of the time the 16-bit address is used. So this is a shorter address known as the node ID, and this is unique within a network, similar to an IP address in the Ethernet world. It's assigned as the node enters the network. It's supposedly unique within that network, but there may be two networks that each have a node with the same ID. But because they're in different PANs, it doesn't matter. That's okay. So it's only unique within the network, where the EUI64 is unique across all radios everywhere. Now, I say supposedly unique with the network address because the network address or node ID is able to change after the node enters the network. It's assigned initially as the device comes in, but because ZigBee Pro uses a random address assignment scheme, it is possible for two nodes to have chosen the same random address. If that ever happens, much like the PANID scheme, there is a method for conflict and resolution. The nodes can notice the conflict and, based on the EUI64 information as a fallback, can agree upon new addresses to use. So the nodes will essentially change addresses at runtime if required to do so based on a conflict. So this ensures that ultimately every node has a long and short identifier for its own address, as well as a long and short PANID related to its network. So again, to tie these back to the EmberZNet stack architecture, in our scheme, the UI64 is pre-programmed by Ember at our manufacturing process, and if you need to override them, please refer to application notes 5031 for the system on chips, and 5041 for the network coprocessors. The node ID is assigned as the stack comes online, so if the ID were to ever change, you would get an application level callback if this ever occurred. Additionally, if you're a device that wants to monitor information about other nodes, some kind of gateway device or network analyzer device, you can actually get notified of other ID changes. So because the ID changes generate some traffic in the network as part of a maintenance process, it is possible to pick those messages up and get notified about them. So there's a mandatory callback, the Ember Stack Status Handler that tells you about changes to your own node ID, and there's an optional ID changed callback that notifies you about changes to others' node IDs. So now we've learned about the node types, the coordinator, the router, and the end device, and the different varieties of end devices. We've learned about the PANIDs, both the 16-bit PANID and the extended PANID, and we learned about addresses, the long UI64 address and the short node ID address. So now you know some additional ZigBee concepts. I'm Matt Dibb, and I hope you learned something.